Hello everyone, and welcome to video 5.3 on electric cells. Here's our first slide as usual on the data booklet reference. So take note of that formula, find it in your booklet. It should be on the bottom left of page 6. Also, I should point out that in this video you will be introduced to another equation which we will be using, but it's not in your data booklet. Now, in the previous section, 5.2, we talked all about various elements of an electrical circuit. There was the voltage source, which is the battery. We had the conducting wires, and we had some kind of a component or a load. Those would be things like fans, lamps, speakers, motors, something that is actually using the electricity into a form that we need. So how do we actually create the battery? That's what this entire section is focused on. What is inside of the battery? How does it work? And is there actually something more happening inside the battery than what we actually looked at in section 5.2? Okay, so first things first, in order to make the chemical cell, also known as the battery, we start with a container of weak acid. And inside the acid, we have two electrodes. Now, these are just pieces of metal, but it has to be two different types of metal, otherwise this won't work. You might remember doing something kind of like this in grade 7, 8, or 9 science, where you grabbed a lemon or a potato and you made a battery. But if you remember doing that experiment, something that was really important was that you had to stick two different kinds of metal inside. A lot of times people stick in a copper penny. Now it's actually made up of zinc, but nonetheless it's still either copper or zinc. So you stick a penny on one side and you would stick some kind of a screw on the other side. And because you have two different types of metal, the electrons would start to flow, of course, when you have the complete circuit. It's the same idea here. Now, why is there even electrons moving freely inside of this acid? Well, acid breaks things down. If you've ever seen the Coca-Cola experiment where someone places a piece of metal inside a cup of Coca-Cola and just leaves it, if you take out that spoon or whatever it is after a long time, you'll see that it has corroded, it has dissolved slowly. And so this is what happens when you expose metal to acid. And the stronger the acid, the more it's going to dissolve. Now, when the metal does dissolve, it enters the acid as what's called a positive ion, leaving behind an electron. Everything that we interact with on a daily basis, whether it's a pen or a water bottle or our fingers or a body, everything is made up of atoms. And in the nucleus of the atom, we have protons and neutrons, and orbiting around the nucleus, we have electrons. And electrons are what can be added or taken away from an atom. You can't take a proton or take a neutron or add a proton or a neutron. If we could do that, we would be manufacturing gold in our basements out of something that costs a lot less expensive from the periodic table. It can be done in very, very high energy particle accelerators, but it takes so much energy to produce this and to actually extract a proton from the nucleus that it totally outweighs any benefit you could possibly get from doing that, as it is right now. So, but the idea is electrons can be added or removed easily. I mean, you prove this every time you slide your feet across the carpet and touch your little brother or sister. If you zap them, that means you accumulated onto your body excess electrons from the surface of the carpet or the rug, and they sat on your body until they transferred to your unfortunate younger sibling. Right? So electrons, when they are added to an atom, atoms are usually neutral to begin with. That means they have no charge. They're not positive, they're not negative. You could say that they have a charge of 0. Right? So if you add an electron or you add electrons, now they have more negative charge. Right? So specifically, if you have one atom and you add an electron, it becomes a negative ion. And if you take away electrons, now it has a more positive charge. So it becomes a positive ion. And that's what's happening here. Right, so an electron is left behind when the metal dissolves, and what's left behind is a positive ion. Okay, so overall in the entire battery, you still have a neutral amount of positive and negative charges, but they're beginning to separate. Now notice here, depending on what kind of metals you have, one metal is going to have a certain structure, the other metals will have a different structure. One of them is going to have more negative, more charges overall, more atoms. And so when it begins to dissolve, it's going to produce more negative charges overall on itself, and it's going to leave behind more positive ions, whereas the other metal might have less positive. Now, with any kind of battery, if you've ever looked at one, you'll notice that one side, usually the one with the little tip sticking out, that's the positive end of the battery, and you've got the negative terminal on the other side. So what constitutes positive and negative? Well, in terms of this electric cell, the negative side is the side that has more negative charge, and the positive side is the side that has less negative charge. So from the point of view of the right, this blue metal piece right here, the red looks positive relative to it. And so that's how we differentiate between the positive and negative terminal. Okay. Now, what does the chemical cell do? At the end of the day, it's there and it's responsible for energy transformation. It converts chemical energy into electrical energy. And then perhaps throughout your circuit, you might have a light or you might have a speaker, and then that electrical energy might get converted to sound energy, thermal energy, light energy, whatever it happens to be. Now, if we connect everything, we close our switch, our electron, oh, sorry, let me go back for a second there. Unfortunately, the animation doesn't seem to be working, but when I do post the slides, please do quickly revisit these slides and the animations to see how they work. But I'll explain to you what it's essentially doing here. This electron is starting from this negative terminal and it's moving through the circuit. And of course, it can only do that once the switch is closed. So it starts from the right side here, goes counterclockwise, ends up on the left side. Right? So it's moving through this entire circuit. We will talk about why it's moving from the positive to negative side inside the cell in a couple slides. But for now, let's just focus on the outside, external to the cell. The question here is, why do the electrons run from the negative to the positive in the external circuit instead of the reverse? So we did address this a little bit in section 5.2. We said that on the negative side, the electrons are negatively charged, so they're repelled from this side, and therefore they're going to move through the circuit, and they're attracted to the positive side. But we can also answer this in a more meaningful way using energy principles, which we will do. Now, there are two types of cells, primary and secondary, as you can see from the title of this section. So we'll get into each of those. Okay, so each time an electron leaves the negative terminal or the negative electrode, the acid creates another electron because as time passes, this is dissolving more and more. Now, each time an electron enters the positive terminal, the acid neutralizes the electron. Okay, so this process keeps going and going until one of the metals is used up or the electrolyte is fully used up. Now, this is the case with a primary cell. A primary cell, you are using up all the chemical reactions, and once all the reactions that are possible to be done are done, nothing else can happen and the battery stops working. So you can't recharge it. Now, we're used to using secondary cells in our daily lives. We have a secondary cell in our cell phones and in our laptops, two of the most prominent places, even in your car. Okay, so that's actually a very big, very heavy battery. Secondary cells involve chemical reactions that can go both forward and backward. And while that may not be very significant for some of you yet, or maybe it is, depending on whether or not you've taken chemistry, once you do take chemistry, this will be very significant for you. Some reactions can only happen in one direction, while others can happen forwards and backwards. Now, a current isn't really just one electron moving through the circuit. You got to think about where the electrons are coming from. Right? So think about what this circuit is made up of. These wires are probably made up of copper or some other nice conductor. Now, copper is a material. It's made up of atoms, atoms whose nucleus contains protons and neutrons and who has electrons orbiting around the nucleus. And it's some of those electrons which are able to move through the circuit. Now, whether it's the electrons in the atoms of copper in the wire, or it's the electrons in the atoms of maybe steel or aluminum in the switch, or in the tungsten in the filament of this lamp, everything is just a huge sequence of atoms. And therefore, there's a huge sequence of electrons. Imagine cars back to back to back, bumper to bumper throughout this entire street. But the difference is it's a chain. So again, unfortunately, the animation is not working in this video, but the idea is when one electron starts moving forward, that moves the next one, which moves the next one, which moves the next one, kind of like a longitudinal wave, actually. And next thing you know, they're all moving. Okay. Now we're going to consider the electrons at positions A and positions B. So notice they're labeled on the electrodes. Both electrons do feel a repulsive force, right? Because remember, this electrode is negatively charged, but so is the blue one. This is also negatively charged. So the question then becomes, why do the electrons move counterclockwise based on the layout of this picture? Why are they moving in this direction? Okay, why do they move from A to B? Okay, so I'll let you think about that for a moment. you need to pause the video, go ahead. Well, the reason the electrons move from A to B is because even though they're being repelled from both sides, it all depends on which side is a bigger repulsion. And because I have more negative charges on the right, there's going to be a huge repulsion here. So this repulsion outweighs the repulsion at B, hence there's a greater push at A, and that pushes the entire sequence in that particular direction. Okay, and that's what's explained on this slide right here. All right. Again, let's consider the electrons at points A and B. Which one has more potential energy? All right, well, usually when we consider potential energy, so far we've always been talking about gravitational potential energy. And we know that the higher an object is from the surface of the Earth, or based on a certain reference point, the more gravitational potential energy it has, and the more potential it has to gain kinetic energy and a higher velocity overall. We also know that generally speaking, potential energy gets converted to kinetic energy. When one is high, the other is low, right? So you're not going to have both of them high at the same time. It just wouldn't work. Now, in this case, we have chemical potential energy or electric potential energy, right? So electric potential energy while it's inside the circuit. So let's stick with that. When the electron starts at terminal A, we know it's feeling a really big push to move through this circuit. Now, in this particular case, we're ignoring gravitational potential energy. So don't look at this in terms of altitude from the electric cell. That's not what's important here. What's important is how far it has traveled through the circuit. Imagine this distance that the electron has to travel through the circuit as its distance towards the Earth, right, in terms of its altitude. Okay? The more it has traveled through the circuit, the closer it's getting to the surface of the Earth, or in this case, the closer it's getting to its equilibrium, which is right here at point B. So when this electron is moving through, it's losing its electrical potential energy slowly, but it's gaining kinetic energy, right? Once it gets to point B, all of its energy has been converted to kinetic energy, and there's no electric potential energy left, right? So the idea is at point A, it's all electric potential energy. All right, now this is something that we talked about in section 5.2, and here's the reason. We talked about conventional current. Even though we understand that current by definition is the movement of electrons through the circuit, and specifically the definition of current is charge per unit time that flows past a certain point per second, we know that that charges the electron, because you cannot just yank protons out of a nucleus and cause them to flow through a chain in some kind of circuit. It doesn't work like that. It's the electrons that are moving. But unfortunately, when the experiments were first being done on electric circuits, it wasn't known which charge was actually the electrical carrier inside of a circuit. And unfortunately, Ben Franklin, who actually had a lot of other notable contributions to science, he unfortunately guessed wrong that it was the positive charge. Well, you know, it was a 50-50 chance at that point, so we just have to go with it, because this is how all the paper and all the literatures were written at the time. They assumed that electrical current is based on the direction a positive charge would move through the circuit. So we just have to remember that we call that conventional current. Right, so on the left, this would be Franklin's cell, and on the right, we have an actual real chemical cell. And really the only difference between the two is in the real cell, it's the electron that's going in one direction, and in Franklin's chemical cell, we just had a positive charge going in the opposite direction. Apart from certain items and certain things, a lot of the mathematics of these two scenarios is really the same. And that's why the positive charge flow, which is called conventional current, is still used in circuit analysis. And so whenever you're asked to sketch in the direction of conventional current, it is the direction a positive charge would move if it was let go and let free inside of a circuit. Okay, now we have positive charges. This is from Ben Franklin's point of view, the old point of view. Which one has more potential energy? Well, remember, there's more potential energy at the spot where it first starts. Now, if we had a negative charge, it would want to start, based on this picture, at location B, and it would want to move through the circuit counterclockwise. But we have a positive charge. We know the positive charge is going to want to move clockwise based on this picture, because it's going to be feeling repulsion from the greater positive charge which is coming from the red electrode, which means, based on this picture, the positive charge has more potential energy at location A. Okay, now we define the potential difference, or the electric potential difference, delta V. So in section 5.2, I often said, well, look at a battery next time you're in your house. The battery might be rated 1.5 volts, it might be rated 9 volts, it might be rated 4.5 volts. Usually it's in increments of 1.5 volts. So if you want to just take a look at something quickly, you can open up your remote control and take a look at the batteries that are inside. You can also take note of whether they're primary or secondary cells. A secondary cell would probably be a better investment at that point. Now, electric potential difference. The reason why we say it's a potential difference is because looking in the electric cell, we have two electrodes, one that has a greater negative charge and one that has a lesser negative charge. So one that looks more positive and one that looks more negative, from the point of view of whatever charge you happen to be looking from. Now, each one of these electrodes has its own voltage. Now, the charge is going to move either from high voltage to low voltage, or low voltage to high voltage, or high to low potential, or low to high potential, depending on whether it's a proton or an electron. So when we compare the two spots, we call that a potential difference. What is the difference in voltage between one of these electrodes and the other? That's why we call it delta V, the change in voltage, right? So this is the amount of work done in moving a positive charge Q from a point of lower potential energy to a point of higher potential energy. This is the formula that is not in your data booklets, but we're still going to be using. So please remember this. So delta V is equal to delta EP over Q. Now, I'm going to cheat here a little bit and tell you that, okay, well, it does kind of exist in your data booklet. I just don't want to confuse some of you, but I think it should be okay. In box 5.1, which we are not covering because this is an SPH3U topic, grade 12 physics, there is a formula right here, a little bit in the middle, that says V equals W over Q. That one single formula is useful, and that's essentially this formula, except instead of W, we have delta EP. However, if you noticed in the slides, the definition says this is the amount of work done per unit charge, right? So that's the potential difference, or that's the voltage. So if you want to reference that formula, go ahead, but please do not use any other formulas from that section. Okay, a lot of times we just abbreviate potential difference as P dot D. Okay, so you'll see that later on in the slides. All right, so what is a battery at the end of the day? Well, think of it like an engine. You need an engine to run your car, and you need an engine to run any other type of electrical circuit. It uses chemical potential energy to take positive charges, unfortunately based on Ben Franklin's analysis, positive charges, and move them from low to high potential within the cell so they can do work. Right? Outside of the cell, we're going from high to low potential, but inside the cell, then you have to complete the circuit. So you have to go from low to high potential. Right? And it's the chemical energy that pushes it through from one electrode back to the initial one again. Now, we do have a schematic diagram of the circuit here, down that's being created in the bottom middle. Now, if this proton was to actually move through the circuit, the switch would need to be closed. So later on, when you actually view the slide, you're going to notice that the positive charge is moving through even though the switch is shown to be open. That's just because that's the schematic diagram for the switch. But you know that the switch has to be closed in order for the charges to move. Okay, this is such a fantastic slide. And again, I sound like a broken record because unfortunately the animations are not working. So when I post the slides, please especially watch this slide, but I'm going to do my best to explain to you what's happening. Okay, so this is an analogy as to how the chemical energy and electrical energy work hand in hand with the kinetic energy. So how does this charge move through the circuit? So we've got this positive charge. And now just imagine this positive charge. Let me see if I can at least get part of this animation going, like with these snippets. Notice that this little drum is moving up and down, kind of like a piston. When it has a little amount of space up here, there's an explosion. When there's a little amount of space at the bottom, there's an explosion, right? Depending on how it moves. There's energy being constantly created. Now, let me go back again. Up. this positive charge is moving through the circuit. So imagine this positive charge is sliding here to the left. Right now its height, right, because we're using the gravitational potential energy analogy, is constant. So because its height or its elevation is constant, its potential energy is constant. And here it's at its lowest potential energy. So what does it do? It enters the cell at its attractive end, and it starts to go up this escalator. I wonder if I can get that in here actually. Hang on. There we go. It starts to go up this escalator. So the battery pumps it up. It gives it potential energy, right? It converts chemical energy into potential energy, giving it the correct potential energy to move through the circuit again. Now, before it actually, hang on a sec. Now we've pumped it up to this high level of potential energy. Notice that its potential energy is constant until it moves through one of these turning wheels. Right? So this would be a component in the circuit, like a fan or a motor or a light or a resistor, whatever it happens to be. When it goes through these components, notice that its elevation is dropping. So the more it's interacting with the component, the lower it's going. So the less its potential energy is becoming. Right, so unfortunately that part of the animation still doesn't work. Now after it passes through the spinning wheel, it has a constant potential energy, after which here, why is it losing potential energy again? Why is it on the slant? Because it's moving through this turning wheel once again. So it's interacting with this circuit component. Once it's finished interacting with the circuit component, it's reached its lowest potential energy once again, and it is free, it reaches the battery, and it pumps up its electric potential energy once again. So this is the chemical engine that drives the battery. This is an analogy after all, right? This is not actually what happens, but this is a fantastic analogy. Please do revisit the slide once it is posted and watch this animation. All right, let's try this example. 200 microcoulombs of charge, and so this symbol mu, remember it means micro, is brought from an electric potential of 2 volts to an electric potential of 14 volts through use of a car battery. What is the change in potential energy of the charge? All right, so let's go to our piece of paper here. Hopefully you have the slides and therefore a question in front of you. Okay, so here we go. Example. So we have 200 microcoulombs of charge. Now micro, if you're not familiar, so you can look that up in your data booklet. And that prefix stands for times 10 to the minus 6. In grade 12, we're going to be working with charges so much more, a lot more calculations with charges, and you're going to see this micro symbol come up a lot. Kind of like I said earlier when you were introduced to light waves at the end of our sound waves unit, I said light waves, especially within the visible spectrum, we express them in nanometers, times 10 to the minus 9 meters. So these are just some prefixes that you get used to in various sections of physics. All right, so it's brought from an electric potential of, so V1 is 2.0 volts, to an electric potential of 14 volts using a car battery. So between V1 and V2, there's a potential difference. So that's V2 minus V1, which is 14 minus 2. So that's 12 volts. Okay, so we have the potential difference, we have the charge, and what we're asked to find is the change in potential energy. Okay, and this is electric potential energy, by the way. All right, so based on our formula that we had, we know that the electric potential difference is equal to the electric potential energy per unit charge. So if you remember that definition, you'll remember the formula. Since we're looking for delta EP, we're going to rearrange this formula for delta EP. So the change in potential energy is equal to the charge times the potential difference. Sometimes this is just called V, sometimes it's called delta V, which I know gets confusing, but it's just how it is. 200 times 10 to the minus 6 coulombs times 12 volts. All right, so what do we get? 200 times 10 to the minus 6 times 12. 2.4 times 10 to the minus 3. Now, this right here, I realize, let me just explain what this is. C, this is the unit for charge. It's called the coulomb. Okay, so coulomb of charge. So here we have microcoulombs of charge. That is the SI unit for charge. So having plugged it in like that into the formula, it is absolutely correct to do so. and volts is the correct unit for voltage and potential difference. Now, energy is joules. Right? So if you plug in SI units, you'll get SI units out. All right, so the change in electric potential energy of the charge is 2.4 times 10 to the minus 3 joules, or you could call that 2.4 millijoules. Back to the slides. All right, electromotive force. If you remember, we actually introduced this in section 5.2. I discussed how it was given the symbol epsilon. This is the Greek letter epsilon, but we call electromotive force a lot of times just the EMF. Okay, so that's what it stands for. Now, as I mentioned in the earlier video, the reason why the battery is sometimes called the electromotive force, or the voltage from the battery rather, is called the electromotive force, is because scientists originally thought, and it's pretty logically makes sense for them to have thought this, that the charges that are moving through the circuit are being pushed. And when you think that something is being pushed, usually it involves a force. So there was some kind of electric force from this sort of motor, and so electromotive force, right? So this is what you get. We now understand that it's not a force that's pushing the electrons through the circuit, it's changes in energy. So the electron is moving from a region of high electric potential energy to a region of low electric potential energy. Hence, it's moving in a certain direction. All right, so we've got our multimeter here. We're going to be measuring the voltage of this battery. So we have to change the dial. Okay, we can see that the voltage of the battery is 1.6 volts. Now, when we're talking about the battery's voltage, we give it a symbol epsilon. So that's what EMF stands for. Just as components in a circuit constitute a voltage drop and the battery constitutes, well, largely a voltage gain, as we'll see in a second, we call the voltage gain of the battery, or the voltage provided by the battery, epsilon. That's how you differentiate between it. A lot of times in my solutions for various electric circuits, I use capital V subscript capital T for total voltage. That is the same thing as this. Although you're going to see in this video why it's important to actually call it epsilon and not V sub T. There's going to be some more stuff that I have to describe. The last thing on this slide is the fact that since there is no component attached to this circuit, it really is just a battery and a multimeter, or in this case, which is acting like a voltmeter. We say that the circuit is unloaded because there are no components. Another word for component is load, right? So this would be your light, your fan, your speaker, your motor, whatever it is that is connected to your circuit. So that was an unloaded circuit. All right, let's try this example. How much chemical energy is converted to electrical energy by the cell if a charge of 15 microcoulombs is drawn by the voltmeter? All right, so we're looking for the amount of chemical energy converted to electric energy. All of the chemical energy ideally is converted to electric energy unless there is loss of energy due to heat, again, as we'll see very soon. Now, we know what the charge is, 15 microcoulombs. We know what the voltage is, it's 1.6 volts. So let's go to our paper and work this out. So really what we're looking for is delta EP. We're looking for the change in potential energy because that is going to get converted to electric energy. Now, again, we know the charge, that's 15 microcoulombs, which is 15 times 10 to the minus 6 coulombs. And we know that the potential difference, or the voltage of the battery, is 1.6 volts. So once again, we're using this formula. We're using delta V equals delta EP over Q. So rearranging that for delta EP, that's Q delta V. All right, so that's 15 times 10 to the minus 6 coulombs. Again, that's the SI unit for charge, times 1.6 volts. So we have 15 times 10 to the minus 6 times 1.6. That's 2.4 times 10 to the negative 5 joules. So this chemical energy is converted to electric energy by the cell. All right, back to the slides. All right, so we enter a new topic now at the top, internal resistance. All right, this is a very important topic. If we connect a resistor as part of this external circuit, now we're going to see something happen to the voltage reading of the battery. notice that it dropped to 1.5. It was at 1.6, but now it's at 1.5 once the resistor is connected. Usually when you connect the resistor to this circuit, we would say that, well, the total voltage in the circuit is supplied by the battery, and the only voltage drop is across this resistor, right? So we saw yesterday what these colored bands represent and how to read it. Now, if this is your only voltage drop, why did the battery voltage drop from 1.6 to 1.5? Well, all of a sudden, this circuit is no longer unloaded. There's a load here. There's a resistor. It's not just a battery anymore. So this circuit is now loaded. So what ended up happening? We now have a potential difference delivered by the battery of 1.5 volts. So something happened that when we decided to connect something to it, the battery all of a sudden couldn't supply as much voltage as it could when there was nothing connected to it. Now, just like any device in an electric circuit, whether it's, like I said, a light, a fan, a speaker, a resistor, even the wires in themselves, everything has resistance. There's no such thing as no electric resistance, unless you're considering superconductors, which if you're interested, look into that. It's very cool stuff, but we're not going to be looking at that here. Just like you can minimize friction as much as you want, even a sheet of ice has friction on it. Even a sheet of ice has coefficients of static and kinetic friction or dynamic friction. You can't get rid of it fully as long as you're in contact with the surface. Now, it's the same thing with resistance. Even though we consider the conducting wires to be ideal wires of zero resistance, there is technically still resistance there. Even the battery, if the electrons are trying to push through the battery, they are going to encounter resistance. There's going to be some kind of loss of energy there, which is unfortunate, but it exists. So what we call that is internal resistance. Internal to what? Internal to the battery or the electric cell. Now, internal resistance is represented with the lowercase letter r. So any other type of resistance, you have to use capital R. Internal resistance only gets the letter lowercase r. Please do not use any other symbols for that. Now, of course, the best cells have the smallest amounts of internal resistance. Right now, something that you should always be careful about is a hot battery. Right? So the longer you use the device that has a battery, the more current that's been going through it, the more it's heating up, the more power it's been dissipating. Right? So if this battery gets too hot, there have been a lot of cases where people actually burn themselves because of the extreme high temperature. So this is actually how we can calculate the amount of energy produced per unit time by the battery. Recall from video 5.2 that power is defined as work per unit time, which can also go hand in hand with energy per unit time. How much energy is expended per second? That is a joule per second, which is also known as a watt. That is what power measures. Now power, one of the formulas we saw in video 5.2 was I squared times R. So if you want to find the power dissipated by the battery, then all you have to do is replace the R in the formula with the internal resistance, lowercase r. All right, let's try this problem. A battery has an internal resistance of 1.25 ohms. What is its rate of heat production if it's supplying an external circuit with a current of 2.00 amperes? All right, so let's work this out. All right, example. So the internal resistance of the battery is 1.25 ohms. Notice it's pretty small compared to the other resistances we've seen. Of course, it's not going to be huge, but it's still there, and it's something that we usually shouldn't ignore. I is equal to 2.00 amperes, and we're looking for the rate of heat production. Something to understand is that in physics, we use the word rate a lot. Rate just means what is the amount of this quantity measured per unit time. So it's the quantity divided by time. It's always divided by time. This is what we mean by rate. So if it's the rate of heat production, so the heat production per unit time, well, what is heat production? Heat production is thermal energy, capital Q. We spent a whole section on this. Q divided by T. What is energy divided by time? It's power. So this question is asking you for power indirectly. Okay, so you have to be able to put those pieces together. All right, so what do we have? All right, so we are looking for P, and we just saw on the previous slide there is an expression, P is equal to I squared times R. Now, in this particular case, since we're dealing with internal resistance, we change this to P is equal to I squared times little r. So that's equal to 2.00 squared times 1.25. So that's 4 times 1.25. So, okay, well, that's 5, sure. So 5 watts. This is how much energy per unit time, or 5 joules per second, that the battery is producing. Let's go back to the slides. Something interesting to note, and this is at the bottom of the page, is notice that because power is proportional to I squared, okay, so that means if you double the current, the power increases by a factor of 4. If you quadruple the current, the power increases by a factor of 16. So just pumping the current a little bit more will incredibly increase the temperature of your battery. It will increase the energy produced per unit time exponentially. Right? So now, this is also very important. If you accidentally short circuit a battery, the battery may even heat up enough to leak or explode. Okay, so this has happened to me in a couple of years ago when I was teaching in Miami. I was teaching AP physics, and one of the batteries began leaking, and it's very dangerous for that to happen, because if you have too much electrical current going through, well, it can't sustain it. So, well, we were lucky it didn't explode, but stuff like this could potentially happen. So you have to be very careful when you handle batteries. You have to make sure they're not expired, because yes, they do expire, and you got to make sure the amount of energy going through is not too high. This is what's meant by a short circuit. If you simply connect the ends of a battery, do not ever do this. This is extremely dangerous, because if you connect the ends of the battery, you're completing the circuit. And so what happens is the electrons, which are leaving the negative side of the battery, are going to rush through this wire to the positive side. They're going to rush through the battery, rush through the wire, rush through the battery, and it's going to move at an exceptionally high speed, a significant fraction of the speed of light. So electrons move through circuits very fast, and because there's no resistor here, no load, no lamp, nothing, there's nothing to slow it down. It's just going to be moving very fast, and that very fast movement of electrons correlates to a high current, which then correlates to a very high amount of energy produced, which, like it says, it could cause the battery to explode. So this is a very dangerous scenario. Please be careful. All right. Now, how do we represent the internal resistance of a cell? We should have some kind of circuit symbol for it. Right, so this is how the circuit symbol for it is represented. This is not in your data booklet, by the way, so you have to remember how this is put together. Right, so we have a regular cell and we have a resistor. We put them side by side with a line in between them, and then we enclose it in a dashed rectangular box. So the fact that these two are enclosed together in the same box implies that they are together. So this little rectangular box inside is the internal resistance of this cell. Okay, so now we understand this to be a unit. And often we also will label them. So of course the cell gets the symbol epsilon for EMF, and my internal resistance gets the symbol lowercase r. Okay, now assume we take our cell with its internal resistance and we connect it to an external cell with its own resistor. All right, now what's happening here? Whatever chemical energy there was from the battery, normally we would just have a voltage gain from the battery, and all of that voltage has to get dropped over this resistor before the electron comes back to the battery. But now there's an internal resistance too. And so if we originally had 1.6 volts coming from the battery, that entire 1.6 volts does not get dissipated across this resistor, because now some of the voltage has to get dissipated across this tiny resistor as well. So what turns out is, instead of having 1.6 dissipated across capital R, we only get, let's say, 1.5 volts dissipated across capital R, and the remaining 0.1 volts gets dissipated across lowercase r. It will be a small fraction of what gets dissipated across the actual resistor, but still it's non-negligible. All right, now this slide is looking at what we consider conservation of energy. Right, so recall the expression for energy, potential energy, inside the cell. The electric potential energy is given by the product of charge and its voltage at that particular point. So if we're looking at the potential energy given by the actual cell, okay, ignoring the internal resistance, E sub P is equal to Q times epsilon, right? Because epsilon is the voltage at that point. Now, like I said on the previous slide, that electrical energy gets converted to other energies when it goes through the resistor. Right? Resistor specifically will turn that electric energy into thermal energy. It gives off heat, which is why it's insulated. It's covered with a piece of ceramic, and ceramic is an insulator. So the potential energy at the resistor is equal to Q times V sub R. V sub R is just the voltage drop at the resistor capital R. And finally, we have a voltage drop. So again, electrical energy gets converted to heat energy at the tiny internal resistor. Imagine it's its own separate component. All right, so we have that equal to Q times V sub little r. So this is the voltage drop across the small internal resistor. Now from the conservation of energy, I have energy supplied by the epsilon, and I have energy dropped over, or energy converted to thermal, by the big resistor and the small resistor. Hence the respective sides on this formula. Okay, so we have overall Q epsilon equals QV capital R plus QV little r. Since Q appears in every single term, we can cancel it out, leaving us with an expression that tells us that the voltage supplied by the battery is equal to the voltage drop across the first resistor plus the voltage drop across the internal resistor. Now what we have to understand is that the current is the same throughout the entire circuit. So whatever total current goes through the circuit, it's the same current that goes through the internal resistor, because that's, after all, once the wire connects back to the battery. Now this is where the formula comes from that we have on our formula sheet that you were introduced to on the first slide of this video. Okay, so from Ohm's law, we know that V sub R is equal to I times R, capital R, and V sub little r is equal to I times little r. And so this expression of epsilon is equal to V sub capital R plus V sub little r, we can write it as epsilon is equal to capital I times capital R plus capital I times little r. And if you factor out the I, because it's the same, you end up with said equation that's in the formula sheet. Let's actually try some problems with this. All right. A cell has an unloaded voltage of 1.6 volts and a loaded voltage of 1.5 volts when a 330 ohm resistor is connected as shown. All right, part A, find epsilon, part B, find I, and part C, find the cell's internal resistance. Okay, now to find epsilon, remember epsilon is the battery's voltage when there is no current running through the circuit. And there would be no current running through the circuit as long as it's not connected to something else. Right, so what is the voltage when nothing's connected to it? It's 1.6 volts. So the answer is right here. It's the unloaded voltage. All right, well, how do we find the current? The current, okay, obviously this is going to be when there's something connected, because otherwise no electricity is going to be flowing, right? So how do we find the current? Well, to find current, we need total voltage, we need total resistance. Okay, so let me just go through this for a second. All right. From the second diagram, we know that the voltage across this 330 ohm resistor is 1.5 volts. Okay, why is that? Remember, if the epsilon value is 1.6 volts, and now you have 1.6, let's say, coming from this, 1.5 of it gets dropped here, but the other 0.1 gets dropped at the internal resistor. So from the point of view of this resistor, this capital R, it looks as though this entire battery in the blue box is only supplying 1.5 volts. But in fact, it's supplying 1.6, but 0.1 is being used here at the internal resistor. Okay? So that means we know the resistance here, right? 330 ohms. We know the voltage, it's 1.5 volts. We can find the current using Ohm's law. Ohm's law tells us that, so let's just jump to the paper for a second. So Ohm's law, and this is part B, Ohm's law says V is equal to I times R. So I is equal to V divided by R. And remember, this is the voltage drop across the resistor capital R. So what is the voltage? We said it was 1.5 volts divided by 330 ohms. Those are both SI units, so we're good to go. So 4.5 times 10 to the negative 3. And and that's amperes. All right. Find the cell's internal resistance. That's part C. So we have to find R. Well, remember what I said before. We know that the entire battery is supplying 1.6 volts, right? And then you've got some internal resistance that's using, it's using some of the voltage. And we know that part of this voltage is getting used up in capital R, part of it's getting used up in little r. So how much is getting used up in capital R? 1.5 volts, right? So that means where's the other amount being used? It's being used in the internal resistance. So 0.1 volts. So I know the voltage drop across little r. How do I find the actual resistance? Well, I have to find the current, which I have. If I know the current going through the big resistor, I know the current going through the battery, hence the internal resistor. So I know the voltage of V, so actually I should call this V sub R, and I know I, 4.5 times 10 to the negative 3 amperes, and so I can find the resistance. Using Ohm's law, V sub R is equal to I times little r. So little r is V sub R divided by I, so that's 0.1 divided by 4.5 times 10 to the negative 3. So that's 22.2 ohms. Compared to the 330 ohms, that is significantly less, yet non-negligible. All right, so there we go, 22 ohms. Part D, what is the terminal potential difference of the cell? All right, so terminal potential difference, it just means how much voltage, or what is the potential difference that is actually coming from the cell overall. So how much voltage is coming from that blue rectangular box, right? So, well, there's two answers here. So we have to be very careful how we word this. When the cell is unloaded, right? So in the first top example, the terminal potential difference of the cell is 1.6 volts. However, once we have a loaded cell, the terminal potential difference is 1.5 volts. That's what is delivered by this big blue box. Okay, so it depends whether you're considering loaded or unloaded, like I said. Now, that is the end of the slides, but I do want to show you one more thing on the sheet of paper. Okay, so this is going to become important for you to understand. It may show up on a later evaluation. So let me show you this. All right, let me grab a ruler. So please grab a ruler as well. Okay, so what we're going to do is we're going to draw the first quadrant of a graph. Okay, so on the vertical axis, we're going to plot voltage, and that's measured in volts. And on the horizontal axis, we're going to measure current, which is measured in amperes. We're not going to put a scale because this is just for you to understand what's going on. So this is a voltage versus current graph. Remember, we always do it in the form y versus x. And this is where you cannot ignore internal resistance. All right, so if you have internal resistance, when there's no current going through the battery, the voltage is epsilon. That's your y-intercept, right? And the more current that actually gets pumped through the circuit, the smaller the voltage is going to be given by the battery. So this is a downwards relationship. Now, how do we come up with an expression for this, and how does the formula that's in our data booklet relate to this? Well, if we look at the formula in our data booklet, so in section 5.3, there it is. Epsilon is equal to I bracket capital R plus lowercase r, close bracket. So let's just write that down first. Let me write it over here. Epsilon is equal to I capital R plus lowercase r. Now what I'm going to do is expand this through the bracket, the I. So epsilon is equal to I capital R plus I lowercase r. Now, what is I capital R? I times R is voltage. This is Ohm's law. But what voltage is this? This is the voltage drop across the entire circuit, not including the battery's internal resistor. right? So if I have either one resistor with resistance capital R, or I have a series and not a series, but a very complex circuit with overall resistance capital R, this would be the voltage drop across that entire circuit. Now, what about I times little r? Well, that's going to be the voltage dropped across the battery, right? So what do we get next? We have epsilon is equal to V plus IR. What I'm trying to do is get this in the form of y equals mx plus b so that you can see how this relates to this graph and what information this graph actually tells us. Right? So if I want something in the form y equals mx plus b, I need whatever is on the vertical axis isolated on the left. I need whatever's on the horizontal axis on the right. Right? So let's try to do that. V is on my vertical axis, so I'm going to try to get that on its own. So if I try to get V on its own, I'm going to subtract IR from both sides. Now, just to make it look a bit nicer, I'm going to write the V on the left. I'm going to put the negative IR first, and then I'm going to write plus epsilon. These two lines are exactly the same, so don't get thrown off by that. Now I'm going to throw one more curveball at you, and that is that I like to write the independent variable second. So right now it's coming first. So I'm going to write this as V is equal to negative RI plus epsilon. All right, so finally we can compare this to y equals mx plus b. And so what I want you to notice is two things. The y-intercept, right? So when current is 0, the voltage of the battery is epsilon, right? So that's the electromotive force. It's the full potential ability of the battery. And the slope of this line is negative of the internal resistance. So the slope here is negative R. Of course, you can't have, like I said, you can't actually have negative resistance because that would be a circuit element that actually pushes your electrons faster through the circuit. And as far as we know, that does not exist. All right, so that is it for this video. Thank you for watching video 5.3, Electric Cells.